All right, good morning, grade 11s, and welcome to the pandemic edition of your friction lesson, actually. And I know that in your course outline it says that friction is towards the end, but actually that's when we would do the lab. I feel like there's not a lot of friction questions in the textbook, so there are several on the assignments that I gave you. And yeah, this is a big lesson, and it's I really wish I could give it to you in person, but we'll do the best we can with this. And I've got some things to show you, and normally I would show you a bunch of things in class, but whatever, we're gonna have to make do with what we have. All right, so first I'm gonna start this off by just reminding you of a couple of things. Okay, so here, if you look at this, I want to remind you what the normal force is. So a normal force is the amount of contact between the surface, let's say like you're standing on the floor, so between the floor and you, okay? And remember, that's the normal force. Okay, so let me just write it down. Okay, these two things are really important when we talk about friction. So normal force is, oh, let me change that to a better pen. Okay. So normal force. Normal force is contact between the surface and the object. Okay. Now, what about, that's the normal force. What about gravity? Okay, well, gravity is equal to your weight. Okay, so the force of gravity is equal to mg. Now, on a horizontal surface, normally these two forces balance each other. So let's say you have a free body diagram of an object. There's gravity like this, and there's a normal force like that, because, let me use a different color. Let's say the object is sitting on a surface like this. Okay, so there's gravity and there's a normal force. If the acceleration in the vertical direction is 0, then what happens is the net force is just equal to, let's say, the normal force minus the force of gravity. I'm going to take up as positive, and that's equal to ma. Okay, and I end up getting 0 here because the acceleration is 0, equals Fn minus mg. And therefore, Fn is just equal to mg. It's equal to the force of gravity. And don't forget, m is your mass in kilograms, and g is equal to always 9.8 meters per second squared. That's the acceleration due to gravity on Earth. Okay, so that's just a little reminder of what the normal force is. It's the amount of contact between you and the floor. Okay, and then what gravity is. Gravity is your weight, and we calculate your weight by just going mass times 9.8, and we do that every single time. Okay, now let's take a look at a couple of things. This, we're going to talk about friction, but it's a specific type of friction, surface on surface. That's when two surfaces are in contact with each other and there's friction between them. Okay, there's two kinds of friction that I'm going to talk about today. There's static friction and kinetic friction. Okay, now the word kinetic implies motion. Okay, and the word static kind of implies that there's no motion, but that's not really true. Okay, let me explain what those two things are, and then I'm going to show you these videos. Okay, these videos, and then I'm going to write down the notes after. Okay, so static friction, like if you, actually let's start with kinetic friction. So kinetic friction, if you just take your hands, and I'm going to put my hands together like this. So I know you can't see my hands, but just picture in your mind. I'm going to rub them together so you can hear me rubbing my hands together. Now, my hands are slipping across each other, and it does create heat. That's kinetic friction. So when the two surfaces are just skidding or sliding or slipping across each other, we call that kinetic friction. Okay? So kinetic friction is when the two surfaces are slipping, sliding, skidding, whatever. Okay? Now, the other type of friction is called static friction. With static friction, the two surfaces are not slipping and sliding across each other, but that doesn't mean there's no motion. Okay, so for example, static friction, very useful. Let's say you're walking or running. You need static friction to do that. So what you do is you push with your foot off on the floor to run or walk. And if there was no friction there, or if it was kinetic friction, you started to slip, then you'd find it very difficult to walk. Okay, so when we walk, we use static friction to walk, and it's very important that you understand that. So like you are moving, but you're not slipping. Okay, so that point of contact between your shoe and the floor doesn't slip. That's called static friction. Picture a car wheel. When a car wheel spins, static friction between the wheel and the floor and say the road actually propel the car forward. So it's static friction that allows a car to move forward, to slow down, to make a turn. That's all static friction. Picture a road that's slippery and the car starts to slide. That's kinetic friction. Well, as soon as that happens, you lose control. Okay, so two kinds of friction, surface on surface. Static is when there's no slipping, no sliding. That's what you use to walk, to run, to start, to stop, to change direction, and so on. Okay, that's static friction. Kinetic friction is when there's slipping and sliding going on. Okay, so if you want a little example of this, let me show you these videos here. Okay, so I found this one online, a compilation of ridiculous drivers and slipping and falling. Okay, so here, mostly it's cars, but let me just start this video. Okay, so just keep your eye on the guy with a bag in his hand there. Oh, there he goes. See, the other person walking is using static friction. He hit an icy patch and turned into kinetic friction, and he slides all over the place, right? Okay, now if you watch in the next video, this car is trying to make a turn, but it's kinetic friction. So he's slipping on an icy road. He ends up hitting the lamppost, and then another car slides into him. Okay, so there you go. That is an example of kinetic friction slipping across that slippery surface. There's very little friction there. It's part of the problem. Here's a guy spinning out. But you see the other cars on the road, that's static friction that keeps them on the road. So when you take away that static friction, when the road gets slippery, okay, watch. This car here is going to fishtail. Fishtailing is when your car does this, and look at the rear wheels, how they're sliding across. There is some friction there, but it's kinetic friction. Okay, and you cannot control your car well with kinetic friction. You need static friction. You need the wheels not to slip. Okay, so I'll show a couple more examples of this, then I'm going to pause the video. Anyway, when they're not slipping, that's a great example of static friction. This guy, when he changes lanes, out there he goes, yeah. So now it's become kinetic friction. You can see he spins out and down the hill he goes. Okay. All right, so maybe just one more. It's kind of fascinating to watch these things sometimes, these dash cam videos. Even a four-wheel drive, you can't just, four-wheel drive doesn't get rid of the laws of physics. So, you know, if you rubber on road, if there's not enough friction, your car will slip, whether it's four-wheel drive, whether it's front wheel drive or rear wheel drive. So don't always be fooled by the market hype, okay, when you're buying a car. All right, the tires do make a difference though. Winter tires, we'll talk about this later, make a big difference in improving the amount of friction, static friction you get between your wheels on the road. All right, so here's this video. It's before your time, Scooby-Doo. All right, so in a typical episode of Scooby-Doo, usually what happens is Scooby, which is the dog, and Shaggy is his buddy here. Those two usually find themselves by themselves at some point, separated from the rest of the gang. And usually they encounter the bad guy, who's usually dressed up as a ghost or whatever the case may be. Now in this case, they're going to encounter that guy, but watch what happens when they start to run. Okay, so there he is. See that right there? Whoops. You can see them running here like this. Okay, that's static friction when they're running successfully. But let me show you again, when they slip, okay, like when they're trying to run, but their feet are slipping, that's kinetic friction. You can see is not very effective when they do that, okay? All right, so static versus kinetic friction. Running requires static friction. If you're slipping when you're running, if any of you have ever played sports on the court and you start slipping and sliding around while you're playing, it's actually kind of dangerous. Like, you can hyperextend your leg or whatever. Let's say the floor is slippery and you want to suddenly change direction. That requires static friction. You hear basketball players all the time, their shoes sort of squeaking. Okay, there's a little bit of kinetic friction as they slip, but there's not much. It quickly turns into static friction. And that's what you want on a court when you're running around, is you want lots of static friction. All right, so let's talk about what causes friction. It's pretty straightforward. Okay, so here I put these diagrams in the notes. What causes friction is when two surfaces are in contact, irregularities, microscopic irregularities in the surface, little imperfections in the surface, as the surfaces are trying to move relative to each other. That's what creates friction, okay, is interactions between these surfaces. Okay, so a floor may look smooth, but in fact on a microscopic level it can be quite irregular, okay? It's kind of interesting, if you have rubber sole shoes on, let's say for example, instead of this block, let's say this thing at the top here was the bottom of your shoe. Well, the bottom of your shoe is usually made of soft rubber. And what soft rubber will do is adhere, like it'll mold into those irregularities in the floor. And that will give you friction, okay? Whether it's static or kinetic friction. Okay, so there you go. Now, friction depends on two things. It depends on how rough these surfaces are. So the rougher they are, the more friction you get. That should be logical to you, okay? So the other thing that friction depends on, though, is the normal force. Now, they use N. I'm going to cross that out and write Fn. So this is the normal force here. The normal force, and I know that looks kind of weird, Fn. Okay, I'm going to cross this out, Fn, and this is a reaction force down here, Fn. Okay, so look, what's happening is the contact between the two surfaces, okay, matters for friction. Okay, so the heavier your car is, okay, makes a huge difference. So one thing, I know that I've been so excited to get a Tesla this year, but the thing about a Tesla, it has a really heavy battery in it. And so that car is heavy. Like if it gets stuck in the snow and you try to push it, you'll see right away. That car might look small, but it's heavy. It's probably as heavy as a minivan, even though it's a pretty small car, right? So, but in fact, that heaviness is an advantage on a slippery road because you get more contact between your tires and the road. The tire and the road are squeezed more tightly together. A very light car, like riding my bike, let's say, a very light vehicle, and you get very little friction there. So this force of contact, how much the two surfaces are pressed together, makes a difference. Okay, and actually, the amount of friction you get depends on these two things. One, on roughness, and two, on the normal force. Okay, so those two things together, that's all we need to sort of account for the amount of friction you get. All right, so let's talk about the two kinds of friction. So there's kinetic friction, and like I said, I'm just going to highlight this. I'm going to zoom in. For kinetic friction, the key thing is the two surfaces are sliding across each other. Okay, so they're in relative motion, which means there's skidding going on. Okay, so here I've got the example. This one's for Paige. Okay, an example of someone curling. Now the stone here slides against the, it's moving this way, and it slides against the ice. Now the ice is got some, I don't know, it's not like skating in hockey. It's not like a hockey ice where it's just very smooth surface. It's got like dimples in it. Okay, the dimples create some friction. And actually you need some friction for this game to work well. Otherwise that rock will just continue to slide off the end of the off the end of the surface every single time, and no one will score any points. So you need a little bit of friction there. Okay. And what they do is they throw the rock and then they sweep the surface to increase or decrease the amount of friction just ahead of the rock. Okay. So that's kinetic friction though, because like that, this rock is sliding across the ice like that. Now here in this example, we see tires. This is not a slippery road, but here you can see the marks left behind as the tires skid across the surface. The truck has lost control here. That's when you get skid marks like this. And yeah, you can see actually it created a lot of waste heat, and now the tires are smoking. They're so hot, okay, that they are releasing smoke into the air, okay, and you'll get the smell of burning rubber. Okay, so anyway, kinetic friction. All right, so now I'm just going to explain in the notes here how you calculate the amount of friction you get with this. So I'm going to just say friction depends. Oh, let me switch back to a different color. Okay, so friction depends now I mentioned this already. 1. So it depends on the normal force, which is the amount of contact between surfaces. Okay, 2, it depends on the roughness of the two surfaces. Okay, now how do you measure roughness? Well, we don't actually measure it. What we do is we do experiments, and we would do this experiment together. It's a really easy experiment to do, where I would tell you to determine like something we call the coefficient of friction between your shoe and say a piece of wood or the floor or something like that. Okay, but since we can't do that right now, I'm just going to do my best to explain it to you. There's something called the coefficient of friction. Now the word coefficient means this quantity that we're going to use has no unit associated with it, so there's no unit of measure for roughness. We just do experiments where we say, okay, how much friction do you get? For example, if I had 2 pieces of sandpaper on top of each other and I'm trying to rubbing them together, how much friction will I get? Well, you can do the experiment and see what happens. Or your shoe, if you drag it across the floor, how much friction do you get? Well, you do the experiment and we determine what we call the coefficient of friction, and that's the experiment we're going to do. So let me show you first the variable that we use for this. I'll put it in brackets. This is a Greek letter, it's mu, okay? And we put a little k next to it, okay, and this is equal to the coefficient of kinetic, that's what the k is for, friction. Okay, the coefficient of kinetic friction. And that coefficient, this is a Greek letter, mu, okay? And it stands for, in physics, we use it for the coefficient of kinetic friction, okay? Which is a measure of how rough the two surfaces are, okay? All right, so let me show you what I mean by this. When we calculate the force of friction, I'm going to put FKF, which stands for the force of kinetic friction. It's just equal to the product of these two things. It's equal to the coefficient of friction, mu k, times the normal force. Okay? So the product of those two things will tell us how much friction you have. Now, in real life, it's a little bit more complicated than that. It depends on surface area and a number of other things. But for high school physics, we just boil it down to this. Okay? Yeah, and that's it. So this is how you calculate how much friction you get when you have surface-on-surface contact between two things. Okay, so it's pretty straightforward. And I want to give you an example of this. Here, let's do a sample problem. Okay, and this is going to combine like what you've learned in the past with what we've just learned now about friction. Let's do an example of curling. Okay, so we'll do like a question about Paige here. Let's say Paige is on the curling team. She's going to throw a rock like this, and I looked up what the coefficient of kinetic friction is between those rocks and the ice. Okay, so let's say for a rock, curling rock that is, on ice, not just irregularly, these stones that they throw. Okay, so a rock on ice, the coefficient of kinetic friction is equal to 0.12. It has no unit. Okay, so it has no units at all. It's not newtons. It's not nothing like that. It's just like a factor. Okay, that goes in front of the normal force. It'll tell us how much friction we get. Okay, so that's actually a pretty low number. To give you some comparison, if you had rubber on asphalt, let's say a rubber tire, you get, of course, a lot more friction there. On dry road, you get about 0.8, okay, instead, so maybe about 7 times higher than this. Okay, so anyway, that's a relatively low number, but it's, it's a slippery surface. It's ice, after all. Okay, so now, let's say Paige throws a stone, which has a mass of, I'm just going to make it up. I'm sorry, Paige, you probably know this better than I do, but like I'm going to make it up. I'm going to say it's 4 kilograms. It's probably heavier than that. I'm not sure. Okay, at V1 equals, let's say 4 meters per second. No idea really how fast they throw these things. It depends on what they're trying to do, I guess. But like, I'm going to say 4 meters per second. Now my question for you is, how far will this go? Okay. Okay. Before stopping. So there's your question. So let's just do it over here. And here, let me show you how this works. Let's say you draw a free body diagram of the stone. Okay, this is after she releases it. Okay, so here's the stone. We just draw a box. And here, the ice is like this. Okay, I use blue. The ice is like this. There's your ice. And what's happening, normally we don't draw the ice in the diagram. The rock is traveling that way, so she's already thrown it. Okay. Now, the free body diagram, there's gravity. Because it's on a surface, there's a normal force. Now, which way would the friction be? Well, the friction, when it's sliding friction like this, is going to be against the motion of the object. So actually, the force of kinetic friction is going to oppose the velocity of the object. And that's going to make the rock slow down. So this confuses students, but listen, when you're moving in the forward direction but have a negative acceleration, you're slowing down, right? And that's what's happening here. The acceleration is backward. It's against the motion of the object. Okay, so you've got this problem here. And what we want to do is we want to find out what the acceleration is, and then we'll be able to use a motion equation. Okay, so step 1, we're going to find A. Let me write that again. Okay, so the way you do that is not using a motion equation. You use Newton's laws. Okay, so here, this acceleration is in the x direction. In the y direction, there is no acceleration. In other words, there's no acceleration up and down. The only acceleration is in the x direction, right? Slowing down as it moves forward. So here's how you find A. First, we're going to find the normal force. Okay, so we do that just by going like this. MAY, so this is in the vertical direction, will equal Fn minus Fg. But this one is 0 because there's no vertical acceleration. So therefore, Fn is just equal to Fg, which is equal to mg. We need the normal force to find friction, right? So now, we're going to look at the x direction. So in the x direction, this was in the y direction here, but in the x direction, here's what we have. We have the net force. There's only one force in the x direction, and it's the force of kinetic friction. Well, we know that is equal to mu k times Fn. And we also know from Newton's second law that ma equals the net force, right? So I'm going to substitute ma for the net force, and this is our formula for friction here. Okay. So now what I'm going to do is plug the numbers in. First of all, I won't need the mass. You'll see in a second, because here, I shouldn't have canceled that out just yet. So let me fix that. All right. I'll show you that it cancels out though. I'm going to substitute this in for the normal force. So it's going to be mu k mg. Now the mass cancels out, and I find my acceleration is just equal to 0.12, which is the coefficient of friction, times 9.8. Okay, so if I just take my calculator, and I'll go 0.12 times 9.8, 0.12 times 9.8, I get 1.18. Actually, I'll keep all the digits, 1.176 meters per second squared. Okay, now that is a negative acceleration, right? And it's negative because it's against the direction of the velocity. All right, so that's step one. Now, step two, how do we find the stopping distance? Well, in step two, to find the stopping distance, okay, what you do is you go like this. V1 equals 4 meters per second. V2 equals 0. Delta D is the unknown we're looking for. A is negative 1.176 meters per second squared. Okay, like that, meters per second squared. Time is don't care. Okay, and then you recognize this. This is just a typical problem that we did in the last unit. So you go therefore V2 squared equals V1 squared plus 2A delta D. So we're still not done with the motion equations, right? We're still using those. So 0 equals 4 squared plus 2 times negative 1.176 times delta D. Okay, now I'll just do it in my calculator just quickly. I get 6.8 meters. So okay, so that's how far that stone is going to travel, and it's going to slow down because of friction and then stop. Okay, so that's a typical problem with kinetic friction, and that's it. Now let me show you another problem. This is from your homework assignment. So while we're doing this, let's go to this question here. Okay, so these questions here, this is one of your worksheets. So let's take a look at this problem here, the free body diagram. Okay, and your job in this diagram is just to fill in the blanks. Okay, now let's do it, and what we do is we'll do it one at a time. So here, let's start with the force of gravity. We know that the force of gravity is mg. Okay, so the force of gravity is mg. Now I know the mass is 5, so I'm just going to multiply that by 9.8. So 5 times 9.8 is probably 49. Now I think so. 5 times 9.8 is 49 newtons. So here this force of gravity is just 49 newtons, right? So we filled in one of the blanks. Okay. Now what about the normal force? Well, the normal force is going to balance the force of gravity. So the normal force is also 49 newtons. Those are almost always the same number. Okay. Well, now that I know how much my normal force is, I know how much friction I have, because the force of friction is the coefficient of friction times the normal force, right? So here's the coefficient of friction. So I'm going to multiply that by 0.1. That's 4.9 newtons. Okay. Now, friction is the only force acting on it. So I'm going to use a different color. That means this thing is going to accelerate in that direction. Wow, that's a really thick. Here, let me Okay, so it's going to accelerate in that direction. Okay, now it could be slowing down. It could be moving that way, but accelerating that way, just like that example of the stone, okay, that we just did. In fact, it's a very similar question. All right, so this here, I'm going to circle it. That is the net force on the object. These two cancel out. Okay, those two, they cancel out. Now they're there, but they cancel out because one's up and one's down. So the net force is just 4.9. So to find, here, first we'll write down the net force. So this is 4.9 newtons, right? And it would be to the left, okay? Same direction as the friction force. So this is the unbalanced force, that force of friction. Now I'm going to divide it by 5. Okay, so 4.9 divided by 5 is 0.98. So my acceleration is 0.98 meters per second squared to the left. Now the way I got that was I just wrote that F net equals ma, and so I divided both sides by mass, okay, and the mass is 5 kilograms, so I divided both sides by mass to find the acceleration. So that's how you do it. So there's another problem with friction for you. Okay, so I wanted to show you that. Now you know how to handle kinetic friction. All right, this video is 31 minutes. That's how long it took me to do kinetic friction. I'm going to save the force of static friction for the next lesson. Okay, I think there's very little in the homework on static friction. I think it's mostly kinetic friction. Okay, so I'm going to get you to go ahead and do that, okay, on your own. Some of these questions here on the second worksheet are quite difficult. Okay, give it a try. I think some of them you could do without my help, but you're probably going to get stuck on a few of those, especially on these pulley questions here. So the pulley questions I'll do in another lesson. Okay, and in fact I have several examples that I'm going to need to do with you. Okay, of pulleys and elevators and trains and stuff like that. Some of the questions are here, and like question number 10, for example, is a kind of a challenging one. Okay, so don't worry about doing this entire assignment. Most of this first one, though, you should be able to do. Okay, so give it a try, see if you can do it. I just want to point out something a little strange. They have strange units here. That just means meters per second squared. Meters per second is the same as meters per second squared. Okay, so don't be confused by that weird notation. It's just the same as we've always done. Okay, so give that a try and see if you can fill in the blanks. So please do this worksheet first, and then you can try a couple of questions on the second worksheet, and then we'll take it from there. All right, so guys, that concludes this video on static friction. So I hope you enjoyed that, and we'll talk again later about static friction. All right.